We're particularly interested in how arrays of surface features can control the way that liquids wet the surface. So when you have a structure like this, but at much smaller scale, sort of the scale of a micron-sized post, the liquid will sit at the very tops of these surface features and be very mobile. In fact, the liquid hits the surface, it will actually spread and bounce from the surface. And you see that in many examples in plants, such as lotus leaves and cactus leaves. Feathers of many birds do this, insects have this property, so it's very common in nature.
That one is just a model that is about 1,000 to 10,000 times larger. We will be testing them in wind tunnels so that to replicate, in fact, high velocity conditions.
Nanostructured surfaces that are much like some nanostructured organisms, and these turn out to be great, for example, to prevent ice formation on airplane wings. And they can go to really low temperatures and water just bounces off. And it's based on surface structure, texture, not chemistry or temperature control.
But maybe even more challenging is designing materials that are not hydrophobic only, but also lyophobic, which means they hate any liquid. In particular, crude oil. These absolutely amazing new technologies where the surfaces are designed to be lyophobic, are designed to be so slippery that any material applied to these surfaces will just slide away with no stain, with no residue. Any crude oil moving around with no stain at all. Any other liquid would do the same.
But now with this liquid slippery surface, we can greatly minimize the energy to transport this crude oil. And in other words, it saves energy and also money and also time. And it's very important for oil industry.
Or just in general in optical devices where you want to have optical window cleaning. A number of these technologies have been already filed as patent applications that originated from discussions and developments of the BCC.